Welcome to the introductory guidance to the quantum mechanics. In today's class, we will talk about what is the particle in box model, class number 13. So, in quantum mechanics, the particle in a box model, which is also known as the infinite particle well or the infinite square well, describes a particle free to move in a small space surrounded by impenetrable barriers. This model is mainly used as a hypothetical example to illustrate the differences between classical and quantum systems. In classical systems, for example, a ball trapped inside a large box, then the particle can move at any speed within this box. And it is no more likely to be found at one position than another position. However, when the well becomes very narrow on the scale of few nanometers, the quantum effects become important and quantum mechanics applied here. The particle may only occupy certain positive energy levels. Likewise, it can never have zero energy, meaning that the particle can never sit still in quantum mechanics. Additionally, it is more likely to be found at certain positions than at other positions, depending on its energy level. The particle in a box model is one of the very few problems in quantum mechanics which can be solved analytically without approximation due to its simplicity. The model allows insight into quantum effects without the need for complicated mathematics. It serves as simple illustration of how energy quantization or energy levels, which are found in more complicated quantum systems, such as atoms and molecules, come about. It is commonly used as the approximation for more complicated quantum systems. So let's imagine this below graph. This is a 2D box of the deep well where the free particle is supposed to be still in this very narrow distance. What is the infinite deep square well potential is, and what is the rigid box is? If the studied system of the particle such as electron has a mass m placed in a one-dimensional position of the fixed box of the length L, then the system or particle has the space of moving in one-dimensional of width equal to L, and this has to be elastically collided atoms with the walls. Elastically means the energy and momentum of this atom is conserved. From the deep well graph, the conditions are as this one here, where U is the potential energy. The potential energy of X equal to 0 for the range of particle motion between 0 and L. Then, if X less than 0 and X larger than L, the potential energy is equal to infinity. Now we have a particle in a well-rigid system moving in length L over the x-axis. Then to be able to describe its motion, we have to find its own wave function from the Schrödinger equation. As we have described before, wave function has the ability to describe the motion and behavior of the particle. Now, as its x-axis moving particle, it is arbitrary, has a zero potential energy, where it's not subjected to any external forces, i.e., it is described as a free particle. The free particle wave function, it has been described in several topics in the previous lectures, as it has a sinusoidal solution or sinusoidal root for the Schrödinger equation. This is wave function, a sinusoidal wave function of x equal a sine of k of x plus b cosine k of x, where a and b are the complex constant. In our model example, a, b, and k, which equals square root of 2 multiplied by me divided by h prime square, are unknown. So in the k equation definition, the constraint of k suggests the requirements of determining the energy needs. From this equation, there is needs to determine the energy for the particle. For the particle to move along the x-axis for space length equal to L. Even though the particle has a zero potential energy, it still has the total amount of kinetic energy to keep bouncing. Then our target is to know the wave function of the particle at the edge position of the well. Then, do we need actually some kind of boundary condition? Yes. Boundary condition is the same boundary conditions of the deep well. Then we need to evaluate the wave function at x equals 0. This is the first boundary. And the second boundary is to evaluate the wave function at x equal L. It's defined before the potential energy of this particle at these boundary barriers equal infinity. As its infinity means we cannot describe the wave function of this particle at the barriers, since its potential energy is infinitely large. There is no way for the particle which is located in the deep well to pass the edges equal x equal 0 or edges equal x equal L, as there is no enough quantized energy by this particle to jump out of the deep well. It has always to stay inside the well, bouncing between the x equal 0 and x equal L. In another word, the wave function psi of x for this particle at x equal 0 and x equal L is also equal to 0, because the probability of particle to be in any place out of any position between 0 and L is equal to 0. If we employ the Schrödinger equation at this stage, this is time-independent Schrödinger equation, we are applying the boundary condition that x equals 0. Then we have the multiplication of potential energy at x equals 0. The wave function at x equals 0 will equal infinity, because there is no particle out of the boundaries between 0 and L. Multiplied by 0, this will result as 0. Then what is the constant value of this solution, or what is the constant value of this sinusoidal solution which describes the free particle in the deep well? Let's start with the complex constant value, which is b here. If x equals 0 and psi, which is the wave function of x, equal to 0, I mean x equal to 0, then the psi of 0 equal to 0, then psi of 0, a sine of 0 plus b cosine of 0 will equal 0 plus 1 multiplied by b. 1 multiplied by b equal to 0 only if b equal to 0. 1 multiplied by 0 is equal then only if b equal to 0. Then we have defined that the value of b will equal to 0. The value of b will equal to 0. Then how about the value of k? As b has already defined and found to be 0, we only have the first part from the sinusoidal solution of the free particle wave function as psi of x will equal a sine k of x in this part. Then at x equal L for the other boundary condition, psi of L will equal a sine k multiplied by L equal to 0. This is another boundary condition. There's two boundary conditions, x equals 0 and x equal L. The wave function for x equals 0 is 0, and the wave function for x equal L is L. To satisfy this formula, there's two possibilities. That it's either a equals 0 or sine of k of L equals 0. To satisfy this equation, there's two possibilities. It's either a equals 0 or sine k multiplied by L will equal 0. But as we have already defined that b equals 0, then if a also equal to 0, we will have both a and b equal to 0. Then psi of x will always equal to 0. In another meaning, the wave function at any position over x-axis and for any value of x between 0 and L will equal to 0 always, and that is not correct. In the same way, probability density of finding particles at any position of x, like the absolute value of psi of x squared, will equal to 0. This is actually this is a contradiction for our initial assumption, to our initial condition that there is particle in the well. So A cannot equal to 0. A cannot equal to 0. But sine of k of L is equal to 0. And this sine of k multiplied by L equal to 0 is satisfied when k multiplied by L equal, it's either 0 by 2 by 3 by 4 by etc. Then k multiplied by L will equal n multiplied by pi, whereas n is 0, 1, 2, etc. In another word, k will equal n multiplied by pi divided by L, and this is after the rearrangement. This k value into the predefined k value, we will have k equal n multiplied by pi divided by L, and if you make the those predefined that k equal square 2 mass E divided by h prime square, as a result the particle energy is equal to E n square h square divided by 8 multiplied by m L square, whereas n it's any number 1, 2, 3, 4, 5, and h prime it's Planck constant divided by 2 pi. From this equation, if we have a particle located in the rigid well system, then it will have some amount of energy E in the quantum mechanics prospect. This energy defined as the quantized energy, and n is the quantum number. The 0-point energy represents the lowest possible amount of energy the particle can carry when quantum number n equal to L. In another meaning, even with the minimum amount of energy, the particle still bouncing, the particle must always have some amount of quantum energy. We have defined the value of B and K for the sinusoidal solution of the free particle located in the deep well. Then how about the other complex constant value? How about the value of A? From the sinusoidal solution, we will have only the first part of the sinusoidal solution as B equal to 0, and we have found the value of K. Just substitute the value of K that we have found in our calculation, and B equal to 0. Using the normalized wave function constraint, as previously, the normalized stated as a condition of wave function to be physically measurable and meaningful, as it has a statistical and probability definition. In general, the probability density shall not pass 100% or shall not be more than 1, since there is 100% probability to find the particle in the wave function. If we discretize the wave function and integrate them, the result must equal to 1. Previously, our plane wave have infinite range defined from minus infinity into infinity, but in our model of deep well, the region of particle is only between 0 and L, and this is the region where the probability of finding the particle is. From the prospect, the integration will equal to 1 as well after we substitute the wave function value as psi of x will equal to n multiplied by pi multiplied by x divided by L into this equation here. We'll have this kind of integration, and the result has to equal 1. After integration, the result is a square multiplied by L divided by 2 will equal to 1. Then a square root of 2 divided by L, it's the wave amplitude definition, the amplitude of the wave produced by bouncing particle in the confined well region. However, the value of A decreases. The value of A decreases if the width L increases, and vice versa.